Now let's do some examples with tying all this stuff together. So let's say we're going to reuse examples here. Claim. Our claim is that for all x in our set 1, 2, we're going to take all the numbers 1 to 10. X is even implies x squared is even. Actually, let's do the opposite. This would be interesting. X squared is even implies x is even. Yeah. So how can we rewrite that with what we just learned? Well, it's real simple, right? We just don't include the domain. We say that's under the hood. We know what we're talking about, and we'd say x squared is even implies x is even. And then here's where mathematicians get really wishy-washy, not in terms of what they actually mean, but in terms of what they say. This, like what people say when they see this, is they might say logically apply implies. Something like that. Implies, logically implies, follows, all that kind of thing. They basically use all the same language they use for the single arrow, just applied to predicates instead of statements, which is a little bit confusing, but from context, it all works itself out. So, yeah, working on our context clues. Who would have thought that would come up in a math class? Yes, this is the real, like honestly, like in the pure world of math, this makes total sense. There's no wishy-washiness whatsoever. But because humans do it, we of course bring in our context and our problems, and we make things slightly confusing. That's how it goes. So, however, does anyone remember another way we can rewrite this, getting rid of these conditional arrows entirely? Anyone? Do anyone remember like what that idea was, at least? We don't know the specific one here, but just like the general idea.
Don't you like make the domain like the x is even, and then I don't know, like there's an example that was like for all x in 2, 4, 31, x less than 10 implies x is even, and then you changed it to for all x in 2, 4, x is even. Wait.
So close.
Oh, wait.
Exactly like that. The
Yeah.
idea is, what is this statement really saying? This statement's really saying, remember, this like if we plug in anything that makes the hypothesis false, the statement's going to be vacuously true. So to prove an if then true, all you have to do, I'll write this down. To prove universal conditional, show that for all x in the domain, so we're kind of going off this definition here, for all x in the domain that make p of x true, has that q of x true. So because that's what it means, right? For this condition will be true. If p of x is false, then vacuously true, whatever. The only way we can fail here, like the thing we really need to show is that if p of x is true, then q of x must follow. So it's a universal statement, it's a for all statement, right? So we can just use method of exhaustion, right? And just go through all the things that make p of x true and show that q of x must follow. So I'm not erasing it too quick. I'm sorry. I totally know if I write that again. The point is exactly, Lauren's exactly right. Or yeah, so that's what you have to do. But the idea is, when you're proving a universal statement true, you don't even look at all the x in the domain. You just look at all the x in the domain that make p of x true, aka the truth set of p of x, right? So you just look at the truth set of p of x and prove that all those x's must also make q of x true. The point is, though, that's the same thing as just saying for all x in the truth set of D, q of x must be true. In this case, it's the same thing as saying for all x in 1 to 10 such that x squared is even. Well, actually, I mean, we can just look at it, right? So 1 squared is going to be odd. So that's not going to make it even. 2 squared is going to be 4, so that's even. 3 squared is 9, which is odd. 4 squared is 16, which is even. We're looking at all the x's that make x squared even. 5 squared, is that going to be the true set of x squared is even?
No.
Nope. Is that the 25? Not going to be there. 6 squared, 36. Yep, it's there. 7 squared, 49. Odd, not there. 8 squared, 64. Yep, it's there. 9 squared, 81. Odd, not there. 10 squared, 100. That is even, so it's there. So this is equivalent to just restricting your domain to this, because those are all the places that will satisfy your hypothesis. So for all x in this set, here the conclusion will happen. X is even. These two, this statement and this statement are saying the exact same, or all of them. All these are saying the exact same thing because these are all the places you have to check anyway. In order to prove this conditional true, you have to check all the places that make x squared even, make sure x is also even. Well, these are all the places x squared is even. So you just restrict the domain to begin with. Anyway, no matter how you think about it, let's talk about how you prove it. So proof. And we'll prove it for all statements, so I have to use
Truth set?
so we're not gonna, well, there are gonna be truth sets kind of underneath all this stuff, but we're not gonna need that here. Method of exhaustion is what I was gonna get at. It just means check all of them, right? So proof, note that 2 squared equals, so let's say, for example, you started with this claim. We know it's equivalent to this. Let's say we're trying to prove this claim right here. So you could say notes, we'll say 1 squared, 3 squared, 5 squared, 7 squared, and 9 squared are odd by observation, and 2 squared, 4 squared, 6 squared, 8 squared, and 10 squared are even by observation. Observation just means we literally did the math and found which ones are odd and even. Okay? Further, two is even, 4 is even, 6 is even, 8 is even, and 10 is even, also by observation. Now, note that this by observation we'll talk about this later. So really, there is a definition for what it means to be even. Being even means you're a multiple of 2, meaning you equal 2 times something. And so later on, later on we're gonna get to a point where if you're trying to prove something's even, you can't just say 2 is even. You have to say 2 is even because 2 equals 2 times 1. 4 is even because 4 equals 2 times 2. But we're not there yet. We're just talking about universal conditional statements. So anyway, if we're here, so we don't worry about, I'll tell you exactly what we have to worry about that. We'll make a code word, and the code word is worry now. That is the exact opposite of what you hear. Like they make T-shirts about like what's that? Keep calm and going on or whatever it is. Like my teacher would be worry now. Now's the time. Anyway, yeah. So we know that all of these are even. The point is, therefore, for any x in 2, 4, 6, 8, or no, in 1, 2, all the way to 10, such that x squared is even, x will be even. Hence, for all x in 1 to 10, x squared even implies x is even. Done. And actually, you know what? Actually, I'm going to say this in a slightly different way. I'll say this. Thus, two squared even implies 2 even. 4 squared even implies 4 even. We're going to keep going like this till we get to 10 squared even implies 10 even. Hence, for all x in 1 to 10, such that x squared, or yeah, for all x in 1 to 10, x squared even implies x even. The point being that this is the predicate here. X squared is even implies x is even. We check that this predicate is true for all these x's, because the one it's not true, it's vacuously true anyway. So you could write it like this. Yeah, and then you're totally fine. Does that make sense? I mean, this is just straightforward. Like right here, we're just literally proving that, we're just showing this predicate is true for all possible inputs. All right, but it's also okay if you write kind of like the first thing I wrote, which is if you say instead of doing that whole thing, instead of showing this individually for every single thing in the domain, if instead you got to this point and you said, thus, for every x in 1, 2 to 10, if x squared is even, then x is even. Done. That's fine too. That's totally fine. But I mean, keep in mind that when we're doing this, we're kind of skipping the step of going through and checking each of the x's and showing it is true that 2 squared even does imply 2 is even. 3 squared even does imply 3 is even vacuously. 4 squared even, you're skipping that step, but it's okay. I give you my blessing. Any questions on this?